Okay, so now 3 p.m. in Japan. So welcome to the third AIP Open Seminar. So before starting our seminar here, I'm showing some important notices about this seminar. So just you can read, but let me just repeat. So reproduction is prohibited, and reproducing all or any part of these contents is prohibited without the author's permission. This seminar is recorded and will be made available on our website. And let us start today's seminar. So thank you so much for taking your time and join this open seminar. This is the third RIKEN AIP open seminar. I'm Naoto Yokoya, the leader of Geoinformatics unit. And today we would like to explain and present our recent activities from Geoinformatics unit. So firstly, I would like to explain the overview of our activities, and after that, our two members, so Dr. Uesato and Dr. Adriano, will present a little bit more details about their own topics. So let me start. So our general goal is to understand what's going on this planet from multimodal geospatial data. So particularly we deal with remote sensing data as shown on the left-hand side of this slide. So ranging from optical data to radar images, and together with map data and also in situ data, which have geocoordinate information. And our goal, our unit is belonging to goal-oriented research group. So our goal is motivated by some key applications in this domain, such as disaster and environmental monitoring. And our tasks are mainly focused on image reconstruction and recognition, such as image restoration or semantic segmentation, change detection, and so on. And our final outcome, so the goal is to really produce useful map in applications such as disaster damage mapping or the biomass and carbon stock estimation. So firstly, probably some of you, or maybe many of you, are not that familiar with remote sensing. So let me briefly introduce what is it. So remote sensing is the technique to acquire the information about the object without any direct contact to the object. And a bit more narrow definition, remote sensing is a technology to measure the physical properties of the surface or atmosphere by sensors mounted on airplane or satellite. So here I'm showing the optical remote sensing. So passive optical remote sensing, probably which is the most familiar for us because it's similar to our eyes. So similar to our eyes, the sensor record their energy distribution with respect to different spectral channels reflected on the surface of the ground. So the energy source is sunlight. And different from our vision, the sensors used in remote sensing can capture and measure the energy beyond our vision. So in a much wider spectral range, we can acquire and record the data. So here I'm showing the video of different spectral channels of the hyperspectral imagery as an example. So video is showing each spectral channel ranging from blue, so visible range, to near infrared range, and also short wavelength infrared range. So similar to our fingerprints, in such data set, at each pixel we can acquire the continuous spectral reflectance, so which is really useful for discriminating different materials of the Earth's surface. So this is one example of remote sensing, and another mainstream for monitoring the land or the surface of this planet is using radar system. So particularly it's called synthetic aperture radar. So in this case, energy source is emitted from the sensor, and we use totally different wavelengths, so much longer wavelengths. Actually, we use microwave, and the signal emitted from the sensor is actually backscattered at the surface of the Earth and then come back to the sensor. So this is totally different from our vision. So images are really different, but there are some great property. For example, we can acquire image under any weather condition, and the SAR imaging is really useful for understanding 3D model or deformation of the Earth's surface. But it's really not easy to interpret. If we look at the image, I will show you some examples. In contrast, optical remote sensing is useful for classification and easy to interpret, but in case of spaceborne sensors, if there is any cloud, and then it will be useless. I will show you example later. And in addition to those optical and radar systems, there is also another type of sensor like thermal imaging, which measure the emission from the surface, so which is quite useful for heat island study, for example. And also LiDAR is another very powerful tool to understand the 3D model of the surface. It's used in light information emitted from the sensor. So this is also active, but the active optical remote sensing. And so far, I'm just explaining remote sensing from airplane or satellites, but there is also remote sensing from the ground, for example, from the ground to measure the atmospheric condition. So we collaborate with the Japan Meteorological Agency in order to improve the quality of such ground-based LiDAR-derived data related to atmospheric condition. But today, most of our topics are probably related to remote sensing images from airplane or satellite. So our group actually started 2 years ago, and we try to address challenges real challenges in those key applications. And one of our key applications is the disaster response. And as you may know, in Japan, there are many different kind of disasters. And also, if we look at the world, every month or almost every week, there is some disaster. So we dedicate ourselves to a real disaster response activities. And here are just a few examples of our mapping products that we contributed through some international disaster response collaboration. So, for example, our task is, for example, to extract the extent of landslides or debris flow or flood, or some classification map of the building damages, and also some inundation depth estimation after or during flooding. And so we closely collaborate with domain experts in the disaster management field and try to figure out the real challenges that is worthy to tackle. And then as a research, we try to develop solutions for those challenges. So I would like to show you just one example of the disaster response. So here is an optical imagery taken from space. It was took by Sentinel-2 satellite operated by ESA, European Space Agency, over Koriyama City before Hagibis. In Japanese, it's Typhoon 19 last year. So it was a really big typhoon. So you can see here is the color composite image assigning RGB for RGB. So it's really natural for us and colorful. And by using spectral information, we can perform classification. But after disaster, particularly after heavy raining, usually it's coupled by cloud. And in this case, as you can see, it's totally useless. So in such a case, we often use synthetic aperture radar because it is an active sensor and it can penetrate the cloud, and we can get the image even with cloud. So, but you can see this is different from our vision. So brighter pixels are actually representing some elevated objects, because so this microwave emitted from the sensor usually reflected on the ground and then reflected again on the facade of the building and then come back to the sensor. So that's why if there is any elevated objects, it looks brighter. For flat object like water, there is no backscattering, so it looks like really dark. So this is the image before the typhoon, and the next slide, this one is the one after the typhoon. So you can see it by switching before and after. You can clearly see many pixels get darker, particularly along the river at the center of this slide. This is because if the ground is filled by water, as I explained, there will be less backscattering coming back to the sensor, so it looks darker. But what's a bit tricky is that for the urban area like this part, if we look at this part, this area where there are buildings get even brighter. This is because if flood happen and then the reflection on the water surface becomes stronger than the one on the ground surface, and then reflected microwave reflected again on the facade of the building and then come back to the sensor. So that's why the backscattering become even stronger and it looks like brighter. So usually space agencies or disaster management agencies show this kind of image. So just assigning pre and post images for RGB and just explain, oh, those colorful pixels like red pixels or cyan pixels are corresponding to flooding. But by using a simple image processing or technique, or if we have training data for flood detection, we can train a neural network to detect flood extent. So for example, this is a result after a simple image processing technique. And we can identify the flood extent map. And this is our, let's say, basic product that we always provide for flood in case of disaster response. And we started our disaster response 2 years ago, and then we understand this kind of binary map is not enough. Particularly in Japan, the requirement for the disaster response is quite high. So for example, if we say, oh, this area is flooded, whether the maximum water level or inundation depth was 50 centimeter or 3 meters, they mean totally different levels of damages. So predicting a bit more detailed geophysical parameters like inundation depths is quite important in this domain. And we work towards that direction based on machine learning and also numerical simulation I will explain later. So anyway, this is our first trial that we applied our technique to the real disaster response to estimate inundation depths, and different colors are corresponding to different depths of the water level, maximum water level. And in Japan, the disaster experts in disaster management, they of course produce inundation depth map by looking at the very high resolution aerial photo and detect the flooded region, and then use this information together with digital elevation model to derive this kind of inundation map as shown on the right hand side. And our result derived from actually SAR imagery based on machine learning actually shows quite good correspondence with what human experts derived by visual interpretation. So we have confirmed the great potential of what we are working on, and I would like to explain what is the trick behind of this kind of technique. So this is just one example of our disaster response. But through such practical activities, we identify the research challenges. And then as a research, we try to address those challenges. And here I'm listing 4 different challenges. And the first challenge is the data sets are always incomplete. So full of missing area, missing pixels or noise, or spatial resolution is limited. So how to address that challenge is really important. Particularly, the objects are very small in remote sensing data, so resolution matters a lot. And for this first topic, actually, I will just explain all the topics, but for more details, the next presenter, Dr. Uezato, will talk about a bit more details about this first topic based on the deep learning without training data. And the second challenge is the data sets are quite diverse. So as you may see from my introduction of remote sensing, there are so many different kind of sensors, and even with the same type of sensor like optical sensor or SAR imaging, different missions have slightly different specifications. So data sets are really different. So if we want to understand the changes and if we have different type of sensors or for before and after changes, how we can understand changes. This is another challenge. And Dr. Adriano will talk about this second topic. And the third challenge is probably it is the case in all the fields, but the lack of training data. So labeling based on field survey is really costly. And in case of remote sensing, field survey is possible, but it's really expensive. So how we can automatically get the label information from in situ data is kind of third challenge that we are still tackling recently. And the last point is the limitation of sensing capability. So just one, what I explained for the flood mapping, such as inundation depths, or for debris flow mapping, the topological deformation information is required for applications, but such information cannot be derived directly from the remote sensing one temporal or bitemporal images. So how to be beyond such limit is our last challenge I would like to briefly explain today. And for this challenge, we try to address this problem by combining machine learning and numerical simulation. So let me go through the first topic. For example, here I'm showing the example of the time series optical image data. So as you can see, due to cloud or sensor failure, there is a lot of missing pixels. And time series multispectral data is a kind of four-dimensional tensor data. So how to recover original signal is the task here. So we actually collaborate with a tensor learning team, which actually presented the activities in the first open seminar of this seminar. So we collaborate with them and develop algorithms based on low-rank tensor analysis to solve this kind of problem and try to improve the reconstruction accuracy. And not limited to the inpainting of cloud, but also deshadowing or denoising of high-dimensional optical imagery or denoising of time series SAR imagery. For various applications, we have developed some algorithms, and we have demonstrated quite good reconstruction performance. For example, this is the one example applied to hyperspectral image restoration. So if we can get rich spectral information, we can do much better classification. But if we get more spectral information, it means we split the light into different spectral channels. So for each spectral channel, the energy will be less. So usually for some bands, the signal to noise ratio is low. So the denoising of such data is quite a basic pre-processing step. And Dr. Wei He developed our algorithm based on non-local self-similarity and also global spectral low-rankness. We could achieve improved reconstruction accuracy while keeping the processing speed much less than the state-of-the-art algorithms. It was presented in CBPL last year. So we're bridging somehow CB community and remote sensing as well in this kind of image reconstruction topic. So for hyperspectral imagery, another problem is the spatial resolution. So as I mentioned, if we split the light energy into different spectral channels, and then to keep a signal to noise ratio, we need to make compromise for the spatial resolution. So for a spaceborne hyperspectral imaging mission, many of them usually have 30-meter ground sampling distance, which means on this slide, on the left-hand side, each pixel is corresponding to 30 by 30 meters. So you can understand it's not a good resolution, right? So if we can get very high resolution and hyperspectral data, we can somehow extend the range of application. So one possible solution in this remote sensing field is the image fusion. So by fusing multispectral high resolution imagery and hyperspectral data, we can create reconstruct high resolution hyperspectral data. So this is what we call image fusion based hyperspectral super resolution. And not only that resolution enhancement, but the punch sharpening as shown here, shown at the middle of this slide, the punch sharpening has been studied for a very long time. It has the longer history than hyperspectral super resolution. So the task is the fusion of high resolution panchromatic imagery and lower spatial resolution multispectral imagery to produce high spatial resolution multispectral imagery. So there are several image fusion tasks, and usually state-of-the-art algorithms are designed specifically for each task. And of course, they work well, but we wondered, is it possible to develop some algorithm, a unified approach that is applicable to various image fusion tasks? And our answer is yes. And this work was done by Dr. Uesato. So the second speaker of this seminar will talk a bit more detail about this guided deep decoder, which was presented in this year's ECCB. So our second challenge, as I explained, it's heterogeneous data. So here I'm showing the practical scenario and want to explain what kind of scenario we can think about. So for example, let's imagine we have SAR imagery and optical imagery and something happened. So this arrow indicate the time. And something happened, for example, some disaster happened and there is some change and we want to understand what happened as soon as possible. So as I explained, due to the all-weather observation capability of SAR images, SAR imaging system, in many cases, we can get SAR image first, and then maybe we need to wait a little bit to get optical imagery. But we want to analyze change as soon as possible. So it means for the testing phase, we only have SAR imagery. And for feature learning or training, we have both SAR and optical. This kind of a bit multimodal or cross-modal problem setting exists in many practical case scenarios, particularly in disaster response. So in this line of research, Dr. Adriano worked on this topic through a particular application of building damage mapping. So he has constructed the world's first multimodal remote sensing database for building damage mapping. And he has demonstrated that significant improvement can be achieved when only SAR image is available after a disaster. So he will talk about this topic as the third speaker today. And the third topic is, as I explained, it's lack of training data. And fortunately, in case of, for instance, in case of regular ground shot images, usually human annotator just need to look at the image. And then if the task is semantic segmentation, they can annotate, right? They can annotate, oh, this is a car, this is road, this is sky, and so on. But in case of remote sensing, the objects are really small and some classes are not possible to distinguish by visual interpretation. And in this case, we need to do field survey. For example, on the right-hand side, I'm showing some example images from SACLAJ database, which is constructed by JAXA for the purpose of land cover mapping. So humans go to many places and they record the geocoordinate, and they also take photo, and they put also a label. So what exists where? So whether this is agriculture or whether this is urban area and so on. So the main idea is that, okay, is it possible to automate the annotation process? So by classifying the ground shot images and then use such automatically classified ground shot images results to other label information for semantic segmentation of the remote sensing data. So let me show you just an example here. On the right-hand side, this is the satellite imagery, multispectral imagery taken by Sentinel-2. On the left-hand side, I'm showing many ground shot images actually taken somewhere else in the area of shown on the right-hand side. So firstly, our idea, the first step is to classify these ground shot images shown on the left-hand side. So we classify those ground shot images into, for example, water, agriculture, or artificial surface, trees and grasses, and so on. So once classify those ground shot label information, then we can propagate such label information to the entire remote sensing imagery using spectral information. And we can create this kind of semantic segmentation map without human annotation, at least within this area. So there are more and more practical challenges in this topic, and recently we are working towards a bit more complex and challenging tasks in this line of research. And hopefully we can report something exciting next fiscal year. And the last topic is about how to break the limit of remote sensing. And for example, for disaster response, from pre and post disaster images, conventional approaches usually derive this kind of change map. So for example, where landslides or debris flow happen, for example. But as I explained, what really needed in the disaster management field is more detailed information, such as inundation depths or topographic deformation. So how we can estimate such information from remote sensing data? And for this topic, we try to address this issue by combining machine learning and numerical simulation. So it's a collaboration with simulation experts in RCCS and also Kyoto University. So here I want to share the just main concept. So from remote sensing image, we can get binary change information, but it's full of errors and also difficult to estimate disaster details. And in another field of research, numerical simulation people can simulate how disaster details will be by setting some input data or parameters. And we can also synthesize some binary information based on simulation results. And we can simulate many different kinds of scenarios, but it takes some time to make the simulation very accurate and fit to the real observation. To get accurate input and parameter selection takes some time. So here is the place where machine learning can play the key role. So together with the slope, so topographic information with binary change information, we can train a regression model. So we can regard the simulation data as training data to construct this regression model. So once we construct a regression model, and then during the testing phase, so if something happened, then we just need to put the binary map as input, and then the regression model can output the maximum water level and topographic deformation. So for regression model, we can use whatever we want, but in this study, we adopted attention UNet, which is an encoder-decoder network with skip connections and attention mechanism. So here are some examples with real data. So for synthetic data, of course it works, but for what's important is for real data. And here is the results for two real disasters happened in Japan 2 years ago and 3 years ago. Then the change detection map shown at the middle is the one that conventional approaches can get. So this is just where debris flow or flood happen. And our approach can successfully estimate the topographic deformation. So it means the blue pixels are the areas where soil eroded, and the red pixels indicate the areas where deposit of soil exist. So by combining simulation and deep learning, we can somehow be beyond the limitation of the remote sensing. And there is also in-painting capability as shown in those green circles. So comparing with, we also have some LiDAR measurements, and we also numerically confirm that our approach somehow works with real cases. And you may wonder, this binary change information, this step looks like a bit ad hoc, because this image analysis step needs to be designed by human. So if we can skip this binary change information layer, that would be nice. But to do so, we need to synthesize or augment the realistic remote sensing images. So we need something here based on simulation. And to do so, we also work on an image synthesis topic, which is led by Dr. Gerald Bayer. Actually, he moved to our startup called Thinspective from this month, and in the last 1 year, he worked on this topic. So the task is to generate photorealistic remote sensing images from the label information and the digital elevation model. And if you look at carefully third row and fourth row, maybe you can realize which one is synthesized one and which one is fake. Which one is real and which one is synthesized. And the third row is synthesized one, and the last row is real images. So you can see some images. Some artificial objects are still, we can distinguish some artifacts, but for natural scenes, it's really difficult to distinguish the real and synthesized images. And this is the results for SAR images. And it's even really difficult for me to distinguish which one is real and which one is synthesized one. And our purpose is to use such technique to augment or synthesize the realistic remote sensing images corresponding to simulation results. And this is the result corresponding to the simulation by changing water level. And you can clearly see that gradually the extent of water expand, and yeah. Also the same for SAR images. You can see the dark pixels are more and more. So our next step is to integrate this kind of technique with our framework so that we can use remote sensing data directly for the inputs of our framework. So those are kind of overview of our activities in the last 2 years. And if you see any potential topics that for collaboration, or if you have any interest, feel free to ask now, or you can also contact us by email. Is there any questions? So there was a question, one question in Q&A, but it's answered. It's already answered. So the one question was, are there any approaches to identify the relationship between RGB and hyperspectral data of the same image? So it's probably related to image reconstruction topic. So the answer is yes. So probably related to this topic. So there is a technique to to estimate a relative sensor function like spectral response function or point spread function. Actually, many algorithms require such sensor function, the relative sensor function, but we can derive such functions only from the observed data. That step is part of the algorithms. So another question is any attempts to make use of Google Maps Street View street maps to aid classification? I thank you for this question, and this is really good point. And I think yes, this is I think about Google Street View. And this is exactly what we are working on. And there are a few attempts to use such Google Street View images, for example, to identify building types, for example, and then try to combine such information with remote sensing data to do the semantic segmentation. And this is really a good point and exactly what we are working on. We are trying to use such Google Street View images to do a bit more complex classification tasks, which can be also only possible by domain experts. So thank you for your question. By the way, I forgot to explain. If there is any question, you can ask using Q&A, or you can also put some comments in chat. And if there is no more question, and let's move to the next presentation. So let me stop the screen sharing. So the next presenter is Dr. Tatsumi Uezato, and he will talk about image reconstruction tasks.
Okay, so today I'm going to talk about the unsupervised deep learning approaches for image restoration. My name is Tatsumi Uezato. So this work is a bit different from the unsupervised learning, which is commonly used in machine learning. I'm going to explain in later. I have to extraction. Okay, so this is the outline of this presentation. First, I'm going to explain the limitations of supervised deep learning approaches. And then I'm going to explain the unsupervised approach for remote sensing images. And then finally, I'm going to, this is a collaboration with the Japan Meteorological Agency. And finally, I'm going to present my recent work, which is called Guided Deep Decoder for Unsupervised Image Pair Fusion. So this work was presented in the ACCB 2020. So first, let me explain the supervised deep learning for image restoration. So image restoration has a diverse problem. I give you two examples here. So denoising and super resolution. For the task of denoising, we have a noisy image, and we aim to recover the clean image from noisy image. And for the task of super resolution, we have a low resolution image, and we aim to recover the high resolution image from low resolution image. And deep learning approaches try to consider the input and output dataset as a training dataset. For the image restoration task, we don't have any ground truth, so synthetic images are often used. For example, in the task of denoising, we synthetically generate noisy images, and then we use a pair of noisy and clean images as a training dataset. And for the task of super resolution, we consider the we have a high resolution image, and we simply apply the bicubic or other some techniques to downsample the image. And then we use the low resolution and high resolution images as a training dataset. Because we consider synthetic images, we can get and produce large amounts of training dataset. And in the control simulated experiment, and this supervised approach can achieve the state-of-the-art performance. However, this may not be appropriate for some real applications. Let me explain about the limitation of the supervised deep learning approaches. The left figure shows that diverse remote sensing dataset. These include a multispectral image, or panchromatic image, or hyperspectral image, as the first presenter explained. And sometimes it is very difficult for us to collect or prepare large amounts of training dataset because of hardware limitation or cost. And different kinds of sensor produces different spatial and spectral resolution. And if the datasets are acquired at a different acquisition time, the characteristics of the images can be greatly changed. So in such case, if we train a model on a specific domain acquired by the specific sensor, we cannot directly apply the model to the dataset in the different domains acquired by different sensors. The question is, will it be possible to develop unsupervised deep learning approaches without using the training step? So recently, there is a very interesting work which is called Deep Image Prior. So the key idea of Deep Image Prior is to use only a single observed image without using any training dataset. The left figure shows the concept of the Deep Image Prior. And Deep Image Prior uses random noise as an input. And we also use only a single observed image as in the loss functions. Then Deep Image Prior is different from the conventional optimization. The conventional optimization in the first line of the equation, E represents data fidelity term, and R represents regularization. So for the regularization, we can also design many kinds of different kinds of handcrafted priors. And Deep Image Prior is different from the conventional optimization in that we use the network architecture as a regularizer. So we assume the network itself has an inductive bias. So by optimizing the parameters of the network architecture, we can produce the smooth image for the task of denoising, or high quality image for the task of super resolution. Because we consider the optimization framework, the Deep Image Prior can be combined with different kinds of loss functions, which can be potentially used for a variety of applications. So as I explained, so Deep Image Prior has a great potential because sometimes we cannot collect large amounts of training data, and sometimes it is also difficult for us to design the handcrafted priors. So I gave you one application of Deep Image Prior for the task of denoising of LiDAR dataset. The LiDAR dataset acquired by the Japan Meteorological Agency. They ask us to denoise water vapor ratio, and water vapor ratio is acquired by Raman LiDAR. And then the measurement is done for each minute, and the figure shows that we combine the measurements of 24 hours. Then we can get the image like the right figure. The image shows that the measurements are very noisy, and they are also missing information, and we don't have any training dataset. So when we don't have any training dataset, it is very difficult for us to apply the supervised deep learning approaches. And another problem is that because we don't know true measurements of the water vapor ratio, so this means that we don't have any prior knowledge about the true measurements. In such case, it is also difficult for us to design the handcrafted priors to obtain clean images. And even if we apply simple conventional regularizer, for example, like a TB norm or something like that one, it tends to overly smooth, and it does not achieve a good performance. So here, I just simply apply Deep Image Prior here, and Deep Image Prior considers the random noise as an input, and also water vapor ratio as an output. And the right figure shows the process of Deep Image Prior, and it starts with a random noise. It gradually converges to the observed water vapor ratio. If we do not stop the iteration, the Deep Image Prior eventually converges to the noisy observed water vapor ratio. By applying the early stopping, we can obtain the optimal image like that one. We found this approach has a great potential for this kind of problem where we cannot train the dataset, or where it is difficult for us to design handcrafted priors. So Recently, this is my recent work, which is inspired by Deep Image Prior. So my work is guided deep decoder, which can be used for unsupervised image pair fusion. This work was presented in this year's ECCB. So first, let me explain about the image pair fusion. So the figure shows the low spatial resolution hyperspectral image. And as you can see, the spatial resolution is very limited. But at the same time, we can get high quality spectral information. This spectral information can be used to differentiate or discriminate the materials. But at the same time, we can also capture the low-cost RGB image in the same location. So RGB image has a high spatial resolution, but for the spectral information is very limited. We have only 3 bands, like the left figure. So there is a trade-off between RGB and hyperspectral image. The key idea of hyperspectral super resolution is to fuse the RGB image and low spatial resolution hyperspectral image to obtain the high spatial resolution hyperspectral image, like the right figure. And also, similar tasks can be considered in the task of pan-sharpening. So middle figure shows a low spatial resolution multispectral image. Again, as you can see, the spatial resolution is very limited. However, we have multiple spectral bands, which is useful to discriminate materials. And the panchromatic image has a very detailed spatial information. However, it has only 1 band. We cannot discriminate the materials by using only panchromatic image. By fusing panchromatic image and low spatial resolution multispectral image, we can obtain high spatial resolution multispectral image. Similar tasks can be also considered of noisy no-flash image. So here, no-flash image can capture natural color of the image, but it is a bit noisy. And if we use flash, we can capture the less noisy image. However, the color of the photo can be changed. So what we want is to preserve the natural color of the no-flash image, and at the same time, the image should be less noisy. So by fusing flash and noisy no-flash image, we can get clean no-flash image. So these tasks share a common goal, which try to enhance the image by using input and guidance images. However, they have been addressed independently. So classical approaches consider handcrafted priors. For example, for the task of hyperspectral super resolution, because hyperspectral has a rich spectral information, but at the same time it's redundant. So we can consider low rankness to explore the property of the hyperspectral image. So how about other tasks? In the task of pan-sharpening, there are many kinds of handcrafted priors. One common handcrafted prior is the spatial smoothness to the hidden high-resolution multispectral image. And for the task of denoising, there are also many kinds of handcrafted priors. A commonly used prior is to consider the spatial consistency between flash and noisy no-flash image. So although these tasks can be very powerful, especially when we apply the specific task, but these prior need to be specifically designed for each task. But as I explained, remote sensing dataset has a variety of dataset and characteristics which can be captured by different kinds of sensors. And each year, we have a new sensor and a new task. And it's not very realistic for us to always design the specific handcrafted prior for each task. So in such case, so deep learning approaches are very powerful in such case, because the deep learning approach can solve different kinds of tasks in a unifying framework. For example, for the hyperspectral superposition, we have to collect the training dataset, like RGB image and low spatial resolution hyperspectral image as an input, and then high spatial resolution hyperspectral image as a ground truth. How about the pan-sharpening? Also in the pan-sharpening, we prepare for panchromatic and low spatial resolution multispectral image as an input and high spatial resolution multispectral image as output. Similarly, for the task of denoising, we prepare for flash and noisy no-flash image as input and clean no-flash image as output. And these deep learning approaches can be very powerful provided so datasets are available. But as I explained, it's not easy to collect large amounts of dataset because of hardware limitation and costs. And in the remote sensing dataset, we have a very diverse sensors which produces different kinds of characteristics. So it's not easy to collect the training data for such case. The motivation of our study is to propose unsupervised deep learning approaches which can solve the different kinds of tasks in a unifying framework. So here, this work is inspired by Deep Image Pair, but Deep Image Pair does not consider image pair fusion. So we just develop a new method which is called guided deep decoder. And our work try to use the guided deep decoder in the optimization framework. So let me explain about the proposed method, the guided deep decoder. The guided deep decoder is composed of two networks. First network is the deep decoder network. So this network starts with a random noise in the left figure, and then extract features. And the features are upsampled multiple times. And eventually, the spatial resolution of the features is the same with the output image. And once we get output image, the output image is evaluated in the loss function. In the loss function, we consider only a single input image and guidance image, and we don't require the large amounts of training dataset. We just simply need one single input image and guidance image. And second network aims to extract features from guidance image. So the network is called encoder-decoder network with skip connection. So this network aims to extract low-level and high-level features from guidance image. And once we get the features of the guidance image, we can combine the features in the upsampling refinement unit. Because as I explained, in the deep decoder network, each feature is upsampled multiple times. For the upsampling, we simply apply the bilinear operation. Bilinear operation assumes neighborhood pixels are similar for all of the locations. However, this is may not be true for all of the locations. So in such case, we can use the features of the guidance image to guide the future. And then we can adaptively change the features by using upsample refinement unit. Similar unit can be also considered in the future refinement unit. The difference is that future refinement unit consider both high-level and low-level information extracted by the encoder-decoder network with skip connections. And once by using the upsample refinement unit and future refinement unit, the output image is constrained by the features of the guidance image, because here in this work, we use the network architecture itself as a regularizer. By using the feature of the guidance image, that we can produce more realistic output image. So this is an illustration of the guided deep decoder for image pair fusion. First, let us consider the hyperspectral super resolution. In the task of hyperspectral super resolution, we consider low spatial resolution hyperspectral image as an input and RGB image as a guidance image. Then we prepare for loss function. The first term of loss function shows the output image should be similar to the spectra of the low spatial resolution hyperspectral image. And then second term promotes the spatial information of the output image should be similar to the spatial information of the RGB image. And here we use guided deep decoder as a regularizer because loss function itself is highly ill-posed. It cannot be easily solved. By using guided deep decoder, we can produce output image like the right figure. And then it starts with a random noise, and then it gradually converges to the enhanced image like the right figure. So how about when we consider a different task? When we consider a different task, we just simply change input and guidance images and loss function. That is it. We can also optimize and change the architecture of the guided DB decoder to achieve the best performance for each specific task. However, the objective of this work is to propose a framework, unifying framework. So we fix the architecture and we use the exact same architecture which was used for the hyperspectral superposition task. So what we change is kind of input and output images and loss function. So in the task of pan-sharpening, we consider low spatial resolution multispectral image as an input and panchromatic image as a guidance image. And again, in the loss function, the output, the spectral information of the output image should be similar to the spectral information of the multispectral image. And the second term promotes the spatial consistency between output image and guidance images. Okay, so how about the denoising of normal flash image? So we can also solve this problem in a unified framework. We just simply change input and guidance images and loss function. So here we use a noisy no flash image as an input and flash image as a guidance image. And for the loss function, the color of the image, output image should be similar to the color of input image. And the right figure shows the process of optimization. And as you can see, we can also observe here the output image gradually converge to the enhanced output image. So the approach is very simple, yet very powerful, and we can solve different kinds of image fusion tasks. So these are results of hyperspectral super resolution. The left figure shows a low spatial resolution hyperspectral image, the input image, and the figure next to input shows a reference. And CNMF and BSR and NSR and NLSTF. So those are methods based on matrix factorization or tensor factorization with handcrafted priors, and UDL and USDN. So these are unsupervised deep learning approach, and MHF is a supervised deep learning approach because we tested a method in the controlled experiment. So we synthetically generate the training dataset, and the synthetic training dataset are used in the MHF. And the guided DB decoder was compared with different kinds of methods. And so root mean square error means how similar between the output image and reference. And SA represents spectral angle, how similar the spectra of estimated output image and reference images. So as you can see, guided DB decoder could outperform other existing methods and even compete with supervised deep learning approaches. We can obtain the similar result also in the task of pan sharpening. The left figure shows the in low resolution input image, and then the figure next to input shows the reference. And again, also here, the guided DB decoder were compared with the method which try to use the handcrafted priors and supervised deep learning approaches. And although the idea is very simple, it can achieve the state-of-the-art performance, as I show you. So these are results of denoising. And left figure shows a flash image, and the next figure shows a no flash image. And as you can see, no flash image, the images are very noisy, and we want to remove this kind of noise. And JB represents joint bilateral method. And as you can see, noise is still contained in the denoised image. And DIP is we use the flash image as an input in the encoder-decoder network architecture. And the guided DB decoder is different from the deep image prior in terms of exploring the features from the guidance image. And DVD can perform at least as well as DIP, also for this kind of task. Okay, so here we propose an unsupervised deep learning framework that uses a guided deep decoder as a regularizer to solve different kinds of image pair fusion problems. And in this work, we just presented the results of hyperspectral superresolution, pan-sharpening, and denoising of no-flash image. However, I believe there are many kinds of approaches and applications where we can potentially apply this kind of method. The one limitation of this approach is we need early stopping, especially when we have to apply the method to the denoising task. So now we are working on that one, and we try to develop a method which can automatically determine automatically stop the iteration and get the optimal output image. And more information, including paper and codes, are available in the following links. If you are interested, please check it. Thank you very much for listening. If you have any question, you can write it down.
So there are already 2 questions
Okay.
in the Q&A.
Okay.
The first question is how to compute the similarity between 2 images of different spatial resolution. Any deep learning methods for this task? So maybe it's related to some image registration or something. So
okay, so first we have to register the images, but here in this work we assume the images are already registered, and I'm not sure if he's talking about evaluation, but if he's talking about evaluation, maybe for the output image should be same for the reference image, and we can directly compare the similarity between the output and the reference image.
There is another comment or question from the same person. So when we perform hyperspectral super resolution experiment, do we blur the original hyperspectral image and use it as input to the hyperspectral super resolution algorithm as low resolution hyperspectral image, or do we have low resolution hyperspectral and high resolution hyperspectral image available? So I think
it depends on the method. Maybe for the supervised deep learning approach, we have to assume that first we need to blur the original hyperspectral image, and then we have to use the low resolution image as an input. And then we get the hyperspectral image, which has the same spatial resolution with the original image. And it may be also possible, like what he said is kind of low resolution hyperspectral image and high resolution hyperspectral image available. So we can, yeah, I don't know. We cannot directly compare the low resolution hyperspectral image and the high resolution hyperspectral image, to my understanding. How about you? What do you think of it? Noto?
So I think the question is mostly about how to do experiments, and for numerical variation, we usually use simulated data. So we need ground truth, right? So we firstly downgrade the original data to produce the input images, and then compare the prediction results with the original data to do numerical evaluation. But the idea of having a real low resolution hyperspectral image and real high resolution hyperspectral image, it's also interesting. And some space agencies actually, they have airplanes and they can do this kind of thing, but we don't have such data at this moment. But if we have such data, then yes, we can do a bit more, how to say, it's a kind of real data experiment rather than simulation-based experiments. So there are 2 more questions, so let's move to the other questions. So did you try GAN in the guided deep decoder? Could you please explain the reason why you choose deep image prior instead of GAN?
Okay, yeah. So this is a very good question. And there is also another approach, which is called Shingan, to address the particular problem, like image in painting or image restoration or something like this. But for this kind of specific task, we have a very detailed special information. And special information is already included in the guidance image. And in my case, we didn't try the GAN in the guided deep recorder, but the approach should be interesting. But at this moment, I didn't apply for it. Yeah.
And the last remaining question is, deep image player is used as one kind of regularizer.
Yes.
My question is that, do we need to train deep image player network? Since there is no training data available, it seems deep image player doesn't need to train. If no training, how to determine the network parameters?
Yeah. So yeah, this is a bit confusing for some people. Yeah, I agree with that. So deep image player is kind of one kind of regularizer. So what we said is training is kind of, yeah, what I said is kind of first training, and there are two steps, training and test step. But the deep image player need like a optimization itself. Yeah. So it is kind of training, but we don't have any testing stage. We directly train the model to the available image. So what we did is kind of simply we just use like a optimization approach, like such as Adam or something like this one, and we automatically determine the network parameters using only a single image. Yeah. So did I answer the question? So it's a bit confusing. But if you have a more question, maybe you can ask me later. Probably I can explain it in more detail.
So one more question is your algorithm applicable to the data pairs like RGB and thermal or RGB and depth?
That's also a very good question. So in my opinion, for the RGB and depth, I don't think this method can be applicable to the fusion of RGB and depth because the RGB and depth are acquired in a different domains. So for example, spatial information of the RGB does not necessarily correspond to the spatial information of depth image. Depth imaging is more like a smooth. But I agree with this kind of like RGB and thermal and RGB and depth are very interesting topic. And actually now we are working on it. Yeah. We also work on similar like a similar approach, but it can be more applicable to other approaches. Yeah. So my answer is for guided deep recorder cannot be applied to the RGB and depth, but there is a technique, definitely technique to be extended to be applicable to such works.
I think that's all of the questions.
Okay.
And yeah. Okay,
Thank you so much.
thank you so much for nice questions. And let's move to the last presentation.
Yeah, hello. I'm Bruno Adriano. I'm the last presenter of this open seminar. And my topic is more oriented it's more wall oriented, and the title is multimodal deep learning for disaster damage mapping. This is the outline of my presentation. First, an introduction. I will briefly introduce what is optical image and synthetic aperture radar, but from the disaster management point of view, especially focusing on urban environments. And then I will show how this data set observed, or how a building damage is observed using remote sensing. And then we'll, of course, introduce some related works in this topic of damage mapping. And then I will show you the data set that we have built for these topics. And then the application, later we will show the application of this data set and the final comments and future directions. So just as a review, as mentioned it in the first presentation, we have several platforms for observing disaster Earth surface. We have from the new one, from the drone one, the UAV, to the space shuttles. But in this case, we decide to use the satellite images, especially two sensors, the optical imaging and synthetic aperture radar. Also as mentioned earlier, this image here shows the main difference between the optical and SAR datasets. As optical dataset are more passive sensor, it depends of the daylight condition, and the synthetic aperture radar sensors are active sensors that they emit their own micro signal. So to show more the difference between two datasets in the urban environment, I'll show these two images. On top, this image shows the area of Tokyo Bay, part of the Tokyo Bay. Actually, RIKEN AIP is located around here. This is the Imperial Palace in Tokyo. And this white square shows the Disneyland. So in the top, we see the optical dataset, the optical image. We can see is, as mentioned earlier, the optical imagery basically follows more the surface properties, the sort of chemical aspects of the surface. As for the SAR dataset, is follow more like a geometric properties. Is basically defined by the roughness of the observed surface. So I've also mentioned it in case of a flat surface or like the ocean, the backscattering is almost zero. That's why we can see black, almost black in these areas. But for areas where the roughness is significantly higher, especially in high density urban environments like Tokyo, we can see very bright areas with very bright spots, like here. That is the high-rise buildings, and here. This indicates high backscattering, high return of backscattering due to several properties of the SAR, such as double bounce or triple bounce. As mentioned, the light, the emitting wave hits the ground and reflects on the facade of the buildings or some structure like a tree or something like that. But differently from optical image, this is the same image, but in a different period. And as you can see, the SAR dataset doesn't change much. It's because it is almost not influenced by the weather condition, as in case of the optical dataset. By a simple changes of time or of clouds, we can see different characteristics of the data. So we try to use these two datasets, optical and SAR, for damage mapping as a complementary information. So here is how building damage are observed in remote sensing dataset. And on top, we can see a ground shot image of one destroyed building. Actually, this image is from a tsunami disaster in Indonesia. This is regarded as a close range photo that is normally used in the computer vision community for some. It could be similar to the dataset of cityscapes or something like that. And below is the area located around that building. This red circle shows the location, exactly location of this building. As we can see in the top, in the cross view photo, is much easier to interpret. For us, we can see this is a building, a destroyed building. Actually, we can see roughly 2 or 3 buildings. But in case of the optical dataset or the remote sensing image, corresponding remote sensing image, is much harder to interpret. The building is very small compared to other buildings. Also, as mentioned it early, in this case, we have very clean images. Of course, this is a very close view of this small area, but due to the weather conditions or other factors, we can normally, or it could be the case that a post-event or pre-event image could be unavailable. But in case of close-range photos, of course, it's a little bit difficult to obtain this such information for the damaged areas or affected areas. We can always refer to other sources like a cloud source or Google Street View if we want to focus on pre-event information. And also, if we see the corresponding SAR image after, before and after the disaster, we can see it's even harder to interpret. If we look carefully, probably we cannot see much difference. We could make a mistake and say this corresponds to the same image or the same data. But if we look closely in this area, we can see that this structure, coastal structure, is being destroyed because the tsunami. You can see here. So that is how we can tell that this is a possible information, a possible image acquired after the tsunami. So obviously, this is much harder to interpret compared to the corresponding optical image. And lastly, and more important, I think more important here is that label. In case of close-range image, it's much easy to annotate. There is large data that's already annotated with building, road, or tree. But in case of remote sensing images, especially for disaster management, it's much harder to annotate, to interpret. We need a field expert to conduct some field survey or visual interpretation and properly label the corresponding degree of damage. So, and we also should clarify that there is no universal standard for annotating damage levels. There are some standards in the European Union or in the US, but there is no uniform, there is no simple class of annotation like a building or roads or trees. So we use these two complementary information, optical image for this damage mapping. For example, in this image here, we saw what is that mean, also different characteristics of optic and side image for observing building damage. One hand, the optical image normally have a nadir view of the area, affected area. That means it basically shows the top view of the building. While SAR image, because the nature of the active sensor, it mainly observes the facade of the building. So if we want to use only optical image to classify this building, this kind of building, we may have some errors since we consider only the rooftop didn't change, but we can see the walls here are completely destroyed. But using SAR information, we can properly or more accurately label this kind of buildings, this kind of damage. So that's why also this map shows two major disasters, two tsunami disasters, earthquakes and tsunami disasters. One is here in Japan that occurred in 2011, and this is the building damage that was produced by this tsunami at that time. And this is the building damage for the Indonesian case. This is the same photo that I showed earlier. As you can see, there are many different features for these two different areas. It's like the building type in case of Japan are more concrete buildings, as in case of Indonesia are more like masonry buildings or wooden buildings. And the level of damage is completely, or it is different. Of course, it's connected to the magnitude of disaster, but in simple words, the labeling this type of damage and this type of damage is require different standard for categorizing the damage level. So based on this experience on the information and how difficult it is labeling the building damage after major earthquake and tsunami disaster, we try to, in this work, we introduce a building damage remote sensing dataset. Actually, it's the first building damage using multimodal information. That means optical and SAR information for building damage. And we also introduce here, using our dataset, CNN-based damage mapping framework to test the performance on our dataset in a real case scenarios. Okay, related works. The XView2 dataset, which was proposed with Good et al. Last year, and it was international competition launched in the CVPR conference. They proposed one of the first multi-temporal optical dataset, considering several events, as you can see, as shown in this map. One particular thing of this dataset is that they collaborated with many private and government organizations. For instance, the MAXA. Now MAXA provide the WorldView dataset, the WorldView optical image for the whole dataset. So this dataset is composed of only WorldView 3 images. And the label for most of the events that considering in these datasets are provided by the FEMA, the Federal Emergency Management Agency of the United States. Of course, there is some other outside the United States. They use also other international agencies like Emergency Copernicus from the European Union and others. And although this dataset has several disaster types, like ranging from earthquakes to flood and wind damage, if we can see carefully, most of the events correspond to flood or wildfire disasters. And also most of these events are located in the United States. You can see here in this map. And here is our proposed building damage datasets focusing on earthquakes and tsunami disasters. Our dataset is also composed of optical and optical image, and using WorldView 2 or 3, depending on the events, and also other sensors like Pleiades or Spot. And this here we show some example of the dataset. This is here for the top image, show the pre-disaster and post-disaster for Indonesia. The middle one for the 2011 Tohoku tsunami, and the bottom one for the 2010 Haiti earthquake. In three different continents, three different areas. And here is the corresponding SAR dataset. We can, in terms of SAR dataset, we also consider different sensors and such different bands. In case of, we have for the 2018 Palu tsunami, we have X band from the Cosmos SkyMet. For the Tohoku, and we have the TerraSAR X band also. And in case of in this case, the Haiti earthquake, we also have the TerraSAR X band. But for other events, we also consider L band from the EROS 2 sensor administrated by JAXA. And then one important feature of our dataset is here, that is multi-temporal and multimodal. We have optical and SAR data combined for several areas, as you can see in this map. And we consider major disasters like earthquakes and tsunami and typhoon that actually are one of the most deadly disasters, according to the United Nations. And we also consider several categories for building damage. Here it shows some examples of the damage. And here this table summarizes the events and the dataset, the corresponding dataset for each event, and the source for the building damage labels. Here we can see on top the pre-disaster dataset, optical and corresponding SAR, and the post-disaster dataset, again optical and corresponding SAR, and the footprint, labeled footprint for destroy, moderate, and survivor class, 3 classes of building damage, or categories for building damage. So if we count the number of polygons for each damage, we of course it depends on the damage, but the type of damage and the area. But our data test is a little balanced. We collected more than 120,000 polygons among of all these events, and here you can see the examples of how each damage is observed in the optical dataset. Here we have the post-event after the disaster and before the disaster. So for the completely destroyed one, we can see most of these buildings collapse, or in this case collapse. And in case of the middle or moderate damage, part of the buildings are still standing, but part of the buildings are collapse or destroy, major damage. And in case of the survivor damage, survivor category, of course, there is no major changes that can be observed. So the specific objectives now using this dataset is to test how multimodal or fusion of SAR optical dataset is useful for damage mapping in the framing as a semantic segmentation problem. Also, we try to test a cross-modal of optical and SAR. So to explain our scenarios, our data modality scenarios, this slide shows 5 modes. The first one, we use a fusion mode. This is ideal scenario for disaster management. That means that before the disaster, we have access to the pre and post, the optical and SAR datasets. Similarly, as post-disaster, we have pre and SAR, pre and post. In case of mode 2, we assume that there is no available SAR information, either pre and post the disaster. So we use only optical image. This scenario using optical dataset is best suited for using CNN-based method, since most of the CNN algorithms are developed for optical or photo information. In mode 3, we consider only using SAR information, one channel, as you can see, it's a grayscale image, pre and post. This is normally the scenario that used for remote sensing method that as a change detection analysis. In mode 4, we assume the more realistic scenario for actually damage mapping, as mentioned it earlier. We assume that we can collect pre-event information, optical image, and we cannot collect the post-event optical image due to several factors, weather condition or time of the disaster, and so on. So we use the corresponding SAR post-event dataset. So this is the real-world scenario for damage mapping. This is most of the cases that we face when we want to rapidly conduct emergency response. And for the final mode, the 5th mode, we try to assume that we can collect all information before the disaster in the archive, like optical and SAR. But similarly to mode 4, we can only collect the post-event SAR information. This is the two last mode, the cross mode, building damage mapping. So here we present our damage mapping framework. Our damage mapping framework is based on a semi-Siamese encoded network. First, we encode the input from the pre-disaster and post-disaster, and then for the decoder, we combine those features and try to put a classification map. This is here shows the main properties of our network. And the main network is based on an attention unit also, and we use the F-score harmonic mean to monitor the training. And we use a weighted cross entropy loss, since we, as showed earlier, our building damage data is highly unbalanced for each class. So for the first experiment we show now, we use random sampling. That means that we sample the training and testing data set among all the events. All the events are mixed and randomly sampling in this proportion: 70% for training, 20% for validation, and the rest for testing. So here are the result for the multi-class classification using random sampling for mode 1 to mode 5. We also compare with the XView the solution. In the challenge that we use the model, the implementation model of the first of the winning solution. on our dataset. So using Fusion dataset, combining optical and SAR, and using optical data give the most highest performance for, as you can see, where our network can distinguish clearly among the three classes. Similarly, the network trained on our dataset for the XView. However, for the mode 3 that only considers SAR dataset, either our network and the network of the XView cannot properly distinguish among the categories, as you can see in the middle of the results. Interestingly, for the mode 4, which is the realistic case for damage mapping, our network outperforms the solution of the XView2, especially is much balanced the classification. You can see we can distinguish the destroyed, the moderate, and survivor class. And similarly, the result we can obtain for the mode 5 that use all available pre-event information, optical and SAR. However, for the mode 5, using the network, the solution network of the XView, it fails to classify the damage. So as you can see, obviously, since we are using CNN algorithms, using the mode 2, we consider only optical information provide the highest performance for building damage. So here is the summary table. This is the result of the building footprint, the building mapping for our implementation, and this is the corresponding for the XView solution. Again, the mode 2 optical images shows almost consistent with the reference data, similarly to the mode 1, which considers fusion mode. But however, for using only SAR dataset, cannot solve, especially the median damage. Mode 4 and mode 5, so for our case, for our mapping framework, show similar results. However, for the case or for the solution implemented in XView2 challenge, it cannot properly map the damage. So one thing that we want to point out that is, even though SAR dataset, which is mode 3, cannot reproduce the middle damage, we can clearly see that it can solve the destroy damage and the survivor damage. This kind of binary classification is also useful for rapid emergency response when we want to know quickly where are the major area, the areas that were affected the most soon after the disaster. Now we change the problem settings. Before we consider a random sampling among all the events, but now we select 3 events, 3 representative events: the 2011 Tohoku tsunami, the 2010 Haiti earthquake, and the recently 2018 earthquake and tsunami in Indonesia. So this event are take out from our sampling. This is considered holdout events, and we use the recent event for training and validation. And then once the model are trained, we test it on these events separately, as you can see here. So here, the first column of the result shows the reference data, the ground truth data, and here show the result for mode 1, 2, and 4. We use only this mode because it shows a much higher performance based on our previous results. You can see mode 1, which is fusion optical and SAR, it's of course giving better result, much consistent result. Mode 2 is also shows good performance, and mode 4, which is our ideal mode for building damage mapping in real case emergency response, also is showing some consistent results. So that means that our dataset is working, our framework is working. We are able to have some moderate or consistent damage mapping based on our table summary. So then we compare our damage mapping. Here some summaries of the results. Then we compared our damage mapping framework with the solution of the XView again, but in this case we use the already model trained using the whole XView dataset, and in two separate ways. So that means that we choose again these three events which are not included in the sorry, we choose only these three events, the Haiti, Palu, and Kumamoto earthquake, because those events has the same optical image corresponding to the same sensor of the XView dataset, which is WorldView 3. And we use the Tohoku event in 2011 because this event is not included in the XView dataset events. So again, we use this is the framework of implemented by this image shows the framework implemented by the XView dataset. In the contents, they use two stages for building damage mapping. The first one is focusing only in extracting the building footprints, and after that they focus in damage classification. If you remember, our method is only one single network that is used for extracting footprints and also building damage classification. That's some difference with the model implemented in the XView challenge. So, and again, we use the trained model of the winning solution, and the model are available in this website. So, also to compare our results, we reclassify the XView challenge label. The original label for the XView challenge proposed 4 damage categories, but in our case, we only consider 3. So we combine the major damage and minor damage as a moderate damage corresponding to our dataset. So this is the mapping result. This is a reference area, the reference dataset for Tohoku event. This is the XView solution, and this is mode 2, only using optical, and this is mode 1, sorry, using SAR and optical dataset. Mode 2 and XView are basically the same problem setting using only optical dataset. And please note that for this case, we select just 3 events of our whole dataset to test against a larger dataset, which is the XView 2. So as you can see, our results are consistent. Of course, a little bit less than the XView dataset, but consider that this dataset this model is trained in a very extensive training set. And as our case, we only use 3 events to train our network. So we have similar values for survival level and destroy level, but our model or our limited dataset still cannot properly solve the model, the intermediate class. So there is some problems in the unbalanced training set. So to conclude, this is the first multimodal and multi-temporal remote sensing dataset that includes several categories. This is as far we can tell. Also, our results indicate that using relatively small dataset, as mentioned earlier, constructed from similar or the same disaster event can accurately recognize building damage and tsunami damage. So again, our findings suggest that combining remote sensing information and machine learning technology can be used for or are powerful to rapidly conduct disaster damage mapping in emergency response. So we have, based on our preliminary analysis of dataset, we have future directions. First is unsupervised domain adaptation. As we can see, some problems of using training in different events and applying to other events is the huge domain gap that there are among the damage or the building characteristics, as I showed earlier, between, for instance, Japan and Indonesia. Also, we identify that we need to understand better the multimodal learning for building maps, extracting better features or better or much rich characteristics of optical and SAR datasets. And the final is also related to the image synthesis. There are several events or older events before the popularity of the SAR, high resolution SAR in the early 2000s, that only have a high resolution optical dataset. One plan is to increase this dataset by generating the corresponding SAR image of those events. So with that, I would like to conclude my presentation. Thank you for your kind attention. If you have any question, I will be happy to answer. Thank you.
Any questions? If you have any question, please write in Q&A. So far, no questions. So maybe the topic was a bit specific, and or people just understand the content. Since it's already.
So one thing that I can notice is, or can mention, is that unfortunately we cannot release this dataset as the XView, but we are open to collaborate to share our dataset to collaboration, to institutional collaboration, if somebody is interested.
Yeah. Okay. Thanks. So if there is no further question, if you have any comments or question, please also contact us by email. And lastly, let me just announce. So this today's seminars was the third RIKEN AIP Open Seminar, and thank you so much for taking your time, and we highly appreciate your participation. And actually, every week we organize this sort of open seminar, and the coming editions are listed here. So in December there are four different open seminars, and we will continue in January, February, and March. So please check out our website, and if you find any interesting open seminar, please register. Only when you register to those events, and then you will get the Zoom link. So if you're interested in, please check them out and register to those events. Thank you again for your participation. That's all for today's seminar. Thank you.